One of the most common misconceptions in the field of phase equilibria or phase diagrams is the difference between a phase and a mixture of phases. So today we're going to use Play-Doh to try to elaborate and explain this key difference. All right, so let's start and let's just look at what we have. So here I have two objects, two Play-Doh balls or cubes, one yellow, one blue. As you can see, they're about the same size. And these are going to be what we use to explain the difference between a phase and a mixture of phases. And with that, we're going to think about this, and we're going to look and relate this to solids. And so in a lot of cases, this relates to metals and alloys, but it can also be ceramics and so forth. So let's take each one of these and just describe them, right? So we've got a yellow ball of Play-Doh, we've got a blue ball of Play-Doh. So these are gonna be stand-ins for, let's say, two metals. So I'll call this one metal A, this one metal B. So these are our two metals. And when they're in contact, right? So once they become in contact, they effectively become a mixture, right? Because we have two distinct phases. We have the yellow Play-Doh and the blue Play-Doh, and each of these has distinct properties. So maybe it's a good time to kind of rewind and just think about the definitions. So what a phase is in our context for phase equilibria is a phase is any homogeneous portion of a system. So when we talk about homogeneous, we're talking about homogeneous down to the atomic or molecular scale. What this means is that it's going to have uniform physical characteristics, uniform chemical characteristics, and so forth. So this is kind of our test to see if something's a phase. So what we can do is we can just, again, separate these and look at the yellow Play-Doh, right? So this we're going to call a phase because it has uniform properties, right? It has the texture, it has the color of this yellow Play-Doh, and we're going to call the blue also a phase because it has a uniform property, physical, chemical, and a uniform color. Right? So each one of these is a phase. And so, like I said, once we kind of put them in contact, they become a mixture, right? And you've all potentially seen common examples that illustrate the difference between a phase and a mixture of phases, or so two or more, with a couple examples, right? So everybody's probably seen the oil and water, right? So oil and water separate as two liquids. You can easily see the differences. They have different properties, different densities. And so that is a mixture. And then the other example would be something like water and salt or sodium chloride. You can put sodium chloride in water, and at the beginning, there'll be the sodium chloride crystals. But if you shake it and allow it to come to its steady state or equilibrium, what we call equilibrium, then this will be a solution, a liquid solution, because the sodium and chlorine have sort of split apart and the water dissolved into their respective ions, and they have a uniform property throughout the solution, right? It's a salt solution. So what we're going to do, though, because I think most of the examples for mixtures, phases are often liquids, I wanted to use this Play-Doh as an example, right? So the idea here is, again, we have our two phases separate, we put them together, and it's a mixture. However, we're going to do the equivalent of mixing the water and salt together and see if we can form a solution, right? And again, think of these, our corollaries of this is metal A, metal B. And so we want to see what happens if we try to mix these together like we would with salt water and see if we can form a solution. So again, I think one of the hard parts in metals is often the idea of what a solid solution is, because it's not exactly what a liquid solution is. All right, so what I'm going to do is I'm going to take these again, put them together, and what we're going to do is we're going to mix them together. So this might take a bit, so I might speed this up, but let's see what happens when we mix these together. I'm going to stop here, and I've mixed this together for a minute or so, and I'm going to see and stop here to kind of talk about things, talk about what's going on. Because again, the example I'm comparing this to is something like oil and water or water and salt. So let's go back and look at and think about the oil and water example. With oil and water, you can clearly see they're separated because the water will stay on top of the oil will stay on top of the water because of the density differences. And so it's very easy to see those. And they're very, big layers when you have a lot of oil, a lot of water. With solids, we can have mixtures of solids, but oftentimes we don't see it, right? It's not like the two yellow and blue Play-Doh spheres that we see here. Oftentimes it's on the microscopic scale. So what I mean by that is if we were to look at this metal mixture under a microscope, we might see distinct layers or phases under the microscope that we couldn't see before. And so I stopped here to kind of show you that, right? Because right now, this mass looks pretty uniform, right? But if we were to zoom in, and even if you start to look at different areas, you can see distinct yellow and blue regions. If you look closer, you can start to see that as well. And so again, if we were to zoom in to this, we could see an example of that. So I think that's an important thing to keep in mind with metals and solid materials is even though sometimes to the naked eye, it might look like a single homogeneous phase, when we look at it under a microscope, we can see distinct layers or distinct regions. So this happens in a lot of materials that look homogeneous. Steel, for example, has distinct phases if you look under the microscope. Different forms of brass, different aluminum alloys can have precipitates. And so there's lots of examples where on the surface of the naked eye, on the macro scale, it looks uniform. But when we zoom in to the microscopic scale, there's distinct layers. All right, so I also want to, do the equivalent of that, and let's kind of open it up, right? And we can see that there is these distinct layers. So this is still a mixture of two phases, right? We can see that this is a mixture of two phases. All right, so I still got some work to do. So I'm gonna go back to the kneading. So we're back and we're here, I think, at our final state. So I've got the rough cube. You should note it's about double the size of each individual because we've mixed it together. Here we have a difference in color, right? You can see that it's kind of a odd green color between the yellow and the blue. But let's, take a closer look because I did this before and we saw streaks. And so we saw a mixture, but let's see if we can see anything now. It looks pretty uniform, right? I don't see anything here. So it looks green throughout, right? So what this is then is this is an example of a phase, right? It's no longer two distinct phases, but it's one phase. And so how this translates to a solid is we have the yellow solid and the blue solid, or A and B as we called them before. Each one of those individually had its own properties, that we represented here by those colors. And when we put them in contact, it became a mixture, but they're, two distinct regions. As we blended it together and kneaded it, you saw that that was mixing the two phases, but it was still a mixture because we saw distinct regions. But ultimately, what we see is a single phase. And what's kind of important here is that if we think about this related to the individual metals, what this is saying is that these are interchanging the yellow and the blue, or A and B, for spots in the solid lattice until we have, again, a homogeneous structure, a crystal structure, which is what we see here. So this is going to have, a blend of properties between the A and B, or yellow and blue, which is why you see it represented by the green color. So for metals, when we think about alloys, the same thing happens. If we form a solid solution like we have here, we have a mix or a blend of those properties here represented by color. But for metal, that could be a change in, or kind of a average of the strengths or the ductilities or the electrical properties or the thermal properties or whatever it is. It's a blend of those two. All right, so that's what we have here. So again, this is now a single phase, and we started out with having two distinct phases in close proximity. And so when we think about it, one of the reasons that this can occur and form a solution is because these things kind of chemically or physically like each other or similar to each other, right? And so these, if this was two metals, these metals would have to be similar in characteristic in order for them to blend like this. Otherwise, they might do something else, like be chemically distinct and still have a mixture or multiple phases together. So that streaking that we saw, that would be like if those metals were dissimilar. And so these are all things that occur in real alloy systems. I highly recommend that you, if you want some more information on why things might form a solution or a mixture, I highly recommend you look at my videos for the Hume-Rothery rules, which is a good follow-up to this. So again, hopefully this helped explain the difference between a phase and a mixture of phases when talking about phase diagrams.